All right, I think we can go ahead and get started. Thanks everybody for joining. My name is Dustin Nest. I am StreamNative's technical trainer, and I'm going to be the host of today's webinar. Well, the title is How We Run a 5 Gigabyte per Second Kafka Workload for just $50 per hour. We're going to go through the details of that in addition to a lot more. We're going to go over some details of a typical Kafka cost structure, as well as how we use the Ursa engine to accomplish this. So it's going to be a fairly technical webinar today. And before we go through the complete agenda, since it is pretty technical, we have some technical people on the call with us today. If I could have Matteo and Pengwei, each of you, to introduce yourselves before we go into the full agenda. So Matteo, if you want to go first.
Thanks, Dustin. Hi, my name is Matteo Merli. I'm the co-founder and CTO in StreamNative, and I'm one of the co-creators of Pulsar, and I'm also the PMC chair of Pulsar.
And,
Anyway,
oh,
Yeah, hi. My name is Hui, and I'm a director for platform at StreamNative, and I'm also a Pulsar, about Pulsar PMC and committer. Yeah, thank you.
thank you so much. So for today's agenda, Uh, first, we're going to go over a little bit about the StreamNative Ursa benchmark report key findings. And I'm going to drop the link to that in the chat so you guys can see the full benchmark, because we're just going to hit on just a couple of details of it before we start to go into more of a technical deep dive. Then we're going to go over the typical cost structure of Kafka, going into an architecture deep dive, and then go through details of the cost-optimized data streaming to lakehouse storage with StreamNative Ursa. So what is StreamNative's approach to solve a lot of those cost structure issues that you have in Kafka, which get us into the great results from the benchmark report. And then we want to make sure that you understand how to get started. So I'm going to drop in the chat the actual link for the benchmark report. So if you want to open that up during the webinar and take a look at more of the details of that, feel free. If you have questions as we go along, instead of using the chat, let's try and use the Q&A. I'm going to keep an eye on that and try and kind of lead Matteo and Pengwei maybe to answer some of those questions as we go along. And if we don't get to all the questions, hopefully at the end we have some extra time. So getting right into the key findings of the benchmark report, which I did just send you the link. So as the title of the webinar is, we can run a 5 gigabyte per second workload of sustained throughput for about $54 per hour. And the key here is that if you look at traditional Kafka workloads, you're going to get much more significant costs to run the same workload. We're going to go into the details of that during the whole webinar and why the Ursa architecture is optimized to reduce those costs. But Matteo, if I can get you to kind of summarize a little bit about this key finding, and then also let's introduce Ursa for anyone who isn't aware of it. And then we're going to get obviously into a lot of details of Ursa as the webinar goes along.
sure. Ursa is a new storage engine we developed in StreamNative, and essentially it is a different way that we can plug and have a different architecture for storage that is optimized for different set of workloads and that is very efficient and very cost effective. There are two parts in Ursa. One is the storage engine. The one is that it's also multi-protocol. So in this case, Ursa can support Pulsar protocol, can support Kafka protocol, MQTT, and AMQP protocols. So it's a multi-protocol and also a pluggable storage infrastructure based on the Pulsar architecture, but it is kind of like deviating on the storage side and on the protocol side. So in this test, we basically tested Kafka workloads using Kafka clients in the same Kafka clients across different systems and the same Kafka protocol workloads essentially. And we compared the cost of the infrastructure that was needed to sustain these 5 gigabytes per second, and we compared the cost of 1 hour of running this test. How much does it cost to run this test for 1 hour? So you have these 5 gigabytes per second sustained over 1 hour. What is the cost in each of these different systems? And we kind of like shown that we can support this workload with only $54 or infrastructure cost with StreamNative Ursa compared to 300 for MSK and almost $1,000 with Red Panda. And we will go through all the reasons, but it is like how we can effectively use the resources in the cloud environment to minimize and to work around the cost structure that you have in the cloud environments.
Mhm. So we'll get into more details of that cost structure as we go along, but I kind of want to break down where the costs are coming for this particular use case before we get into more details of the overall cost structure of running a Kafka cluster. So if I break down the cost structure here, you can see that the StreamNative cluster was around $54. And then there's corresponding costs for MSK and Red Panda. And if you look at the EC2 server and EC2 client instances, the cost of running those for this test, they're very similar across all three, where MSK is a little bit more for the server because they're charging for additional things as well. And we have a little bit of S3 request. But what you can see here, where most of the cost savings comes from, is that the interzone client server traffic and interzone replication traffic is 0 for StreamNative Ursa. Whereas for MSK, you're going to have that client server traffic. And then for Red Panda, you have both the client server and the replication traffic. And we're going to get into an architecture diagram, but first, before we do that, Pengwei, can you go ahead and describe a little bit about why MSK has such a high cost for interzone client server, and Red Panda has both for client server and replication, while StreamNative Ursa's is 0?
Yes, sure. Yeah, for like MSK, actually there is no like internal cluster replication. Sorry, it's just no internal traffic for the internal data replication. But like from the client side to server side, you will still have the internal traffic from producer to brokers, because like one partition, you will only have one owner in the cluster. Like it depends on like which zone the owner like served for the partition. And then like if your application, your producers is deployed in different available zones, actually you will have like almost 66% of the internal traffic. And from the consumer side, yes, actually you can config like the consumers to only fetch data from the local zone. So it's from the like benchmark result. It's we also like enable the local zone data consuming for the consumer side. So yeah, this is only for the like producer to broker. And for Red Panda, yes, it's from client to server. It's almost the same, but Red Panda still has the like the internal cost from like broker to broker replication. Yeah, that is the major difference with Ursa. Like there is no client to server internal traffic and no like replication internal traffic. Because like Ursa, there is no like a single leader limitation for one partition. It's actually in different available nodes. You will have like different brokers to serve one partition, so that like the in one available node, the producers and consumers can talk to your local broker directly without any internal traffic. Yes.
Yeah. So it looks like for MSK, they don't charge anything for replication. And then for Red Panda, because they do have to replicate across availability zones, that charge goes into your infrastructure charge. And then there's no guarantee for both MSK and Red Panda that your client will connect to a broker within the same availability zone. So you potentially end up with interzone traffic, or you will end up with interzone traffic. So I guess the key here is that for StreamNative Ursa, to reduce the interzone replication, we use the object storage backend, as Matteo had mentioned. And then to reduce the interzone client server traffic, we guarantee that clients will always connect to a broker in their same availability zone. So those two major architecture changes was what brings the cost down so much. We're going to get into a diagram of this and talk about this a little bit more to visualize it. But I want to talk about beyond just what is mentioned in the blog post of the 5 gigabyte per second workload. There's additional costs that you can end up with as well that Ursa optimizes on top of the ones we've already discussed. So the first two we've already talked about are the interzone client server and the interzone replication. But storage costs, depending on how long you keep your data, can also be a significant cost. So if you're saving data into a solid state drive, that can be significant. So that's going to depend more on your retention than necessarily on your throughput. And Ursa would help to optimize that with object storage. So we're going to get into that as well. Over provision compute, because Ursa, this is something we're very well aware with Pulsar as well, but with Ursa, because the broker is provisioned separately from storage, which is as needed in S3, there's no need to over provision and you avoid any need for rebalancing. And then if you'd like to share your data with external applications, and these days it's very common to want to store data into Iceberg or Delta Lake and to share data into Snowflake or Databricks, you'd have to deploy connectors and save additional copies of the data, which is going to have additional overhead. So I want to go beyond just what we're talking about in the blog post into all the overall costs. And if we take a high level look at what a diagram might look like to accomplish the producers and consumers sending data with multiple availability zones, this is what a typical Kafka architecture might look like. And then to get the data out, the connectors may have to connect to brokers in different availability zones and have large amounts of interzone traffic, and then store additional copies in external things like Databricks or Snowflake. So of those cost drivers here, we have interzone data transfer, which expensive disk-based replication, over-provisioned compute, connector overhead, and duplicated data copies. So I would like to go over each of these in detail with the diagram to really visualize this. So starting with interzone data transfer, we've talked about it a little bit, but now you can really see how the data moves across zones. These first few, Matteo, if I could get you to explain a little bit further on the interzone data transfer and how you can start to introduce how Ursa resolves this again.
Sure. So if you're looking at the traditional Kafka brokers, they're based on electing a leader for a given partition. So when you want to publish data on that partition or to read data on that partition, even though on the read data can be relaxed a bit, but on the publish side, it is always going to be that you have to connect to that broker that is currently the leader for the partition. And if you're deploying your Kafka cluster across multiple availability zones, you got to spread out these brokers across all the available zones. In this case, we may have 3 zones, say A, B, and C. Now you write to the leader, and the leader will replicate so that you have the data available in all your availability zones. That's the key idea. Your application might be in one of these AZs. Now, depending on where your broker is, if you're very lucky, it might be on your same AZ, but most likely it might be on the other AZs. So to talk to those partitions, you have to cross the AZ boundary, and that it is where you're getting charged by cents per each gigabyte that you are transferring across the AZ boundaries. So this is the first one. So when you consume, then you're gonna get another one. So it's already 2x of the traffic, right? Mm-hmm. That can be across availability zones. And this is the client to broker traffic. Kafka itself is doing data replication across brokers. So you write to the leader will push it to the followers, and then it gets transferred across availability zones there 2 times at least. So basically you have another 2x broker to broker data traffic there. So we are already at 4x. So if you're sending like say 100 megs per second, you're already crossing the boundary for 4 times that. So it's 400 megabytes per second crossing the AZ network boundaries. And you can see that because of these multipliers, it can become significantly very quickly, right? Also, if you have multiple consumers of the data, that also like you have multiple copies out, that is also crossing the boundary multiple times. So it can become quickly the most dominating factor there in the cost.
If we can go on to the next cost driver, the expensive disk-based replication.
Yes. So essentially what's happening here is that you're storing the data 3 times in Kafka because of how the replication is set, and you're going to end up with 2 guaranteed copies, but you have to write 3 copies. And so you have to provision the storage to be able to store this data 3 times. And if your retention is not non-trivial, also because Kafka only has time-based retention, you have to say at least several hours to days or a week or 2 max. But there's going to be require a lot of disk space, and you have to keep those disks online. And these disks typically are going to be EBS or persistent volumes, and you're going to get charged by the storage size, and they're very expensive. And you have to keep it 3 times, right? Not just once. You have to keep it 3 times. So that ends up in a lot of cost just to keep these around, these persistent volumes or EBS volumes.
And then if we can go over the third one, the over-provision compute.
Mm-hmm. The third aspect here is that by the Kafka architecture is not very dynamic in the way you can scale a Kafka cluster up and down. Actually, it is very rigid because the partitions are tightly coupled on the brokers, and because the data is stored in these volumes that are owned by this broker. So if you want to scale up your cluster, you have to do a partition rebalancing, which is a very expensive operation because you have to kind of like copy the entire data of the partitions into a new broker. And that is also a lot of cost because you have to ship over the network all that the entire history of that partition, like the full, say, 1 week of data that is stored in that partition, just to rebalance and scale up your cluster. When you scale it down, it is always also the same. You have to rebalance the partition. So rebalancing, it is a very invasive operation in the cluster. If you're trying to do that on a cluster that is already maxed out, you can, or like getting everything in a non-healthy situation, and it's very costly as well. So in the end, what most people end up doing is that you over provision. So you're not scaling up and down your cluster based on, say, on weekly traffic fluctuations. Instead, you're going to say another provision for the peak and over the peak. So if my peak usage is 100, I will have to set my cluster for way over 100. Also for accounting growth trends, right? So if your application is onboarding new user every week, you cannot set at your sizing of the Kafka cluster at the peak for today. You have to set it at the peak for 6 months down the road at least, right? So that you don't have to scale up your cluster manually and incur in these operations every other day. So that end up in a lot of wasted resources because you have to over provision all the time and pay for these resources up front, and then resources that are not going to be needed all the time.
Thank you, Matteo. Pengwei, you finished answering a few questions just in time, I see, for you to go over the next couple things. Next, we're going to go over connector overhead and duplicated data copies. And for those of you who are listening, obviously, we're going to get to the Ursa diagram shortly after we go through this, so you can really see how Ursa resolves a lot of these cost issues. So next up for Pengwei, the connector overhead.
Yeah, I think this is also a very good question in the QA. Yeah, it's I think the question is asking like what is the difference between like WebStream and Ursa? Yeah, I think this is also related to this part. Like if you have the case that you need to like connect the data from Kafka topics to like Databricks to Iceberg, like Snowflake, yeah, actually you need to like set up the like connectors, Flink or something like streaming processing like to connect the data and try to convert the like Kafka format data to columnar format data, and then data will be available like available in Snowflake or Databricks. Yeah, so like in this case, like you must like manage like so many connectors of link jobs like to if you have many like topics, and there is also like the from the connectors like you are able to like avoid the internal traffic, but you need to like set up your like connectors of link jobs it's correctly like with the correct I remember it's just the a feature like to get the like the availability zone information from link context or something. Yeah, it's just I'm not sure like how many people will do it correctly. Yeah, and so yeah, these major two like overheads from the connectors, like managing the connector and the cost from like the internal traffic. Yeah, and yeah, for the next part, I think it's just like you will also have like duplicated data copies, like from Kafka topic to Lakehouse. Yeah, like for example, like your Kafka topic has like a data retention for 7 days maybe, and Lakehouse maybe has like 30 days or something, but they're still like the duplicated data copies like which Ursa is like different with like all the I think all the systems we know it's like a WebStream or upstream or something. It's Ursa just they use the open like house format as the main storage. Like like it's like a Kafka topic can also like read data from Lakehouse directly, like without any like data copies. It's the one single copy of data and available for both streaming read and tables. And that is the major difference here.
So for number 4 with connector overhead, it sounds like the connectors are going to require additional resources,
Yes.
CPU to run them. And they may incur interzone traffic depending on if you set it up correctly so that connectors read only from topics that are in their availability zone. But even if you set that up correctly in Kafka, the reading or you're still going to end up with the overhead and the management of the connectors. And then you're actually making another copy of the data because you're sending it over to Databricks or Snowflake and saving an additional copy over there, which is going to have additional costs.
Yes, correct. And in Ursa, actually, I mean, in Ursa, like it's not like connect the data from Kafka topics to like Lakehouse. It's just like converting the data from S3 object to another S3 object, just like a different format. So it will not like zero internal traffic. Yeah.
So I think that means it's time we're probably ready to switch to the Ursa diagram to really show the simplified architecture and how we drive down all 5 of those major cost drivers for a Kafka implementation. So I want to start again on the left, and we'll go with Matteo again to go through the first 3. So if we can start with what we're saying is the leaderless architecture, but in fact, what we're doing is getting the whole goal of this is to get rid of the interzone data transfer.
Yeah. So the we explained before that in the traditional Kafka model, you have to go where the leader of given partition is, right? We try to kind of like turn around here the problem as in that if I have an application that is in the AZA, I want this application to clients to be talking with a broker that is in AZA as well. So I don't want to cross the boundary because the partition is owned by some other broker in a different AZ. Instead, what we do have here is basically an AZ-aware ownership, leadership. So we have a leader per each AZ. What it ends up being is that you can publish and consume data from a broker in your own AZ so that client to broker will never cross the AZ boundary. And internally, the broker will kind of like use metadata to serialize the events in the stream, and so that the same ordering is guaranteed across the board as well before, and but without the data being moved across AZ. So the broker will just use the Lakehouse native storage and the write-ahead log, writing directly on cloud storage on S3 or GCS. So it will not use data replication across brokers. Instead, we just base on the cloud storage replication, so that we don't cross the boundary there, and at the same time, we can have these multiple brokers writing on the same stream in a safely manner.
So it's not that it's basically that application 1, application 2, application 3, in all cases, they could be writing to the same topic. It's just they're always guaranteed to write to a broker that's in their same availability zone.
Yes.
Yep.
So the write on the same topic through different brokers.
Yep. And then it's kind of gone in this diagram. There's no interzone traffic for data replication. Where did that go?
That is based on the cloud storage, right? So basically, the broker will not use network and local volumes for data replication. Instead, they will just write on cloud storage, and that is what takes out that cost of interzone replication between broker to broker and data replication. The cost it is already factored in the cost of the request we are making to the cloud storage.
So when you write to S3 in that case, the cost of S3 request, which for us was, I think, like $20 some or something like that for the hour, out of the, it was about half the cost, I think, to run the server.
Mm-hmm.
Inside of that cost is already included the fact that S3 will replicate data and make it available across all availability zones. Correct.
So the data is like replicated 3 ways already and across multiple availability zones. And that's it, and that's factored in. So
next up, the number 2 is Lakehouse native. So this is similar to the data storage story that you just mentioned, but instead of reducing the cost related to replication, this is just simply the fact that we're using Lakehouse or S3 or object storage instead of solid state drives, correct?
Correct. So we don't have to provision and pay for this whether we use it or not. And we don't have to over provision disks to keep a long buffer for storage capacity based on peaks and high peaks and low peaks. We just like pay for what we use in the cloud storage side.
So when you delete something off of S3, basically, you no longer are paying for that, and the second you need something, S3 is always available.
Yes.
Yep. And then finally, for Matteo, the stateless and auto scaling. So how do we reduce the need to over provision?
So basically, like in Post, we already had auto scaling before, but this is taken to a further level, as in that there is no local storage anymore here. So it makes for us very easy to go from a tiny broker to a cluster of 1,000 brokers, just purely based on auto scaling up and down, right? It is like there is no local state kept for the data, so it makes it very easy to just increase based on the current load in the cluster. So if you have a traffic spike, the brokers will go up. and we'll be able to sustain the traffic spike. When traffic spike goes down, we can take these brokers and VMs offline because they're not needed anymore. And the operation of scaling up and down, it is seamless and transparent.
And I think we talked about this, or you and I had a discussion about this yesterday. You probably want to keep at least one broker per availability zone, so applications will always be able to find a broker that can service their topic locally without having to cross interzone. But as soon as you have a spike in traffic, you can spike up, or you can increase the number of brokers per availability zone to handle that traffic.
Yes, and that's very common for multiple use cases that you have very a huge difference between the low peak and traffic, more than sometimes like 100x. So it doesn't really make sense to have like if you are say in finance, you have lots of traffic during market hours and zero traffic during weekends or on night time, right? So it is a very common part. So it doesn't make sense to keep the resources online 24/7.
And that's why I wanted to get into these additional cost factors, because the benchmark report is at a sustained workload, but in fact, Ursa works really well also for spiky workloads for scaling things up and down, which is going to have additional cost savings beyond what's just mentioned in the benchmark.
Correct.
Moving over to Pengwei, this is a really exciting part. You mentioned it on the previous slides, but direct streaming to Lakehouse. So we've completely gotten rid of that connector architecture and need for copying the data. I love this box here that says Iceberg or Delta Lake because it's still part of the Ursa cluster. Can you explain how that works?
Yeah, it's I mean actually for like the reason like why we yes, right, it's a two part. It's one is like even you like do not use the open lakehouse format. Actually, you still need to do like data compaction. It's because like in Ursa architecture, like multiple the data from multiple topics will be write to like one S3 object. Is because the reason is to reduce the like API call to S3. So like but after like you have like the what we call war log, and then after a few time, like you will need to like compact to a like topic based storage or directory or something, and then like there might be like two choices. So one is just the like just like compact as the raw format data, and another one is that we can just leverage the lake house. So like user can like get the data by table API directly, and yeah, so and there is no no duplicated data copies. Yeah, so this is why we choose like Lakehouse as the main storage.
Yeah. So basically, we initially write into S3, correct? In the Ursa format.
Yes.
We need to write very, very quickly so that we can acknowledge the data back to the producers and say, hey, it's stored in S3. But regardless of what you're using for catalog integrations, we are going to compact the data into a columnar Parquet file. And then those files are going to be, if you do historical reads on your streams, you're going to be able to read that data.
Yes.
But the beauty of it is that exact same copy of the data that is in Parquet format, so you're storing one copy of the data, is what gets registered in the catalog integration. So if you want to go into the last and final step of reading the data with Databricks or Snowflake or AWS3, what does that look like?
Yeah, it's I mean, in this part actually we have two like models. It's one is like a managed table. For managed table, that means like data is managed by like Kafka topics, like data retention, and the data will not change. It's just like the same as the data you write into the topic, and yes. So for this case, like we will not allow like users to change any data to the table. Yeah, another model is like external table. Um, in this model, it's just like a connector, but we will not like read data from post a topic again, just like S3 to S3. So in this model, like users are able to like do the update to the tables. But in this model, like you will have duplicated data copies, but yeah, but just like for different use cases. Yeah.
Yeah. So for the managed table, there's one copy of the data. It's stored locally inside of Ursa, and the
Yes.
Databricks or Snowflake, you basically are giving it permission to read into the Ursa backend storage.
Yes.
And that's what we're calling a managed table because it's managed by us. For an external table, we basically make an additional copy of the data inside of like an additional S3 bucket that Databricks has access to. And then they're responsible for managing, or you're responsible as the user on the Databricks side of managing like data retention and things like that, because that's a copy of the data that you're now responsible for.
Yes, correct. Like like this is mapped to like major two use cases. So one is like you don't need to update your like raw data. Another case like yeah, you want to do any like updates to your tables. Yeah.
And then as StreamNative's technical trainer, I've made a ton of videos on this stuff. If you go, if our listeners go to the YouTube StreamNative Academy channel, you can find demo videos. I've done actually not just demos, but actually show you how to implement this. It's very cool because for something like Databricks, if you create a new topic, or actually just start writing to a new topic, the compaction service that creates the Parquet files automatically picks up that new data. And once you've done the initial registration of Databricks to Ursa, the data is immediately, once those compaction files are made and registered into the catalog, which is an automatic process as well. You can query it in Databricks or Snowflake. So it's very cool that when I do the demos, I start publishing, and then within like 30 seconds, a minute, the compaction service picks it up, and you can start querying things in Databricks. And the data is still available to be read as a stream inside of Ursa, all from the same copy of the data. So there's tons of demos and implementation videos I've made on doing that as well. So that's why I say that box of Iceberg or Delta Lake is very exciting because I get to make lots of demos on that. So we've gone through all five of the major cost drivers of Kafka and what they look like, and then how Ursa resolves all of them. So just to kind of summarize it, the benchmark report really focused a lot on the first two, the interzone client server and interzone replication traffic. And those were resolved with Ursa by going to a leaderless architecture. And then by using object storage, we get rid of the interzone replication. Because object storage automatically will make that data available across availability zones with no additional cost beyond, for instance, the S3 requests. What we didn't focus on as much in the benchmark report are there are additional cost drivers. So things like storage cost. Ursa uses an object storage backend. So if you're going to store the data long term, that object storage is going to have a significantly less cost than a solid state drive. It also saves data automatically in Iceberg or Delta Lake format in your Parquet files. And you can use them directly in Snowflake Open Catalog, Databricks Unity Catalog. We also have optimized compute. So a typical Kafka cluster would have the potential you'd have to over provision for spiky workloads. Again, that doesn't show up in the benchmark report, but we can get rid of a lot of that over provisioning cost because of stateless brokers, and you can scale up the number of brokers per availability zone. And then the last one was the cost of connectors, interzone traffic, but also CPU to run those connectors and manage them, and then potentially having to make additional copies of the data if you want to use it in external applications. But because we have built-in open table format, all of that additional overhead is taken care of by the compaction service, which automatically takes the data and puts it into Parquet files, which are then, you can register those into your catalogs so you can view the data. So we want to make sure you know how to get started. So the availability of the products currently, StreamNative Ursa is available on BYOC. So it's going to run in your own cloud provider. It's GA on AWS and currently in public preview on GCP and Azure. The catalog integrations, so Databricks Unity Catalog is currently in public preview on AWS and GCP. Again, I've made a ton of videos on this stuff, so you can see it all in action if it's something you're excited about. And Snowflake Open Catalog is in public preview on AWS, GCP, and Azure. There's a $200 free credit to get started, or you can contact StreamNative to book a demo. I'm going to put a QR code up in just a minute. And we are also more than happy to help you get up and running with a BYOC cluster and help you run benchmark testing to make sure that you're running them correctly. Again, there are some special configurations required to make sure that your Kafka clients only write to a broker that's in your availability zone. And that's where that huge amount of cost savings comes in. So we want to make sure that you run the benchmarks correctly. I'm going to drop into this one first. So we also have Data Streaming Summit Virtual 2025 on May 29th. There's a QR code here for those of you who are interested, because I want to leave the next slide up as we go into anything else with Q&A. So I'm going to leave this one up here. This is the QR code to get started on the $200 free trial. And that is good for a BYOC cluster as well. BYOC, again, you're going to have to provision the resources into your own cloud provider, that infrastructure, and then the Ursa cluster will run on top of that. It's pretty exciting because then you can see all the S3 buckets where all the Parquet files are stored, and that's where you register the catalogs. And then if you want to book a demo, I'd actually say that's a pretty good option as well. The sales team would reach out to you and gather some more information about your use case and make sure you get started correctly for exactly what your use case is. So I think that's a great option. Let me paste in the link, but it's also there on the bottom of the page to book a demo. And while I leave that up, I think there were 2 questions in the Q&A. No more have come in, but before we end the webinar, and if anyone else drops in any questions, Pengwei or Mateo, did you want to make any comments on the questions that you answered? Pengwei, I think it looks like you answered both. Did you have any other additional comments on those?
Yeah, I think one note is, it's not contained in the previous benchmark. It's after that we also do a benchmark testing with the connecting the data to a lakehouse with columnar format. We use GR tools to generate the data with schemas, because before we used open messaging to run the benchmark, but there is no schema support for that too. After we tested with GR tools, actually store the data as the columnar format. It will reduce 4 times storage size. It's compared to enable data compression from the producer side. Yeah, so
in addition to using object storage, the storage size is much less when you use a Parquet file, is what you're saying?
Yes, correct. Yes. Actually, I mean, it depends on the your schema. I think if you are just write the byte data, I don't think it will help. That's almost the same. But if you have multiple columns, yes, it will reduce a lot. Yeah.
No, but that's very important, because for schema, that when I've been using Databricks, Unity Catalog, and Snowflake Open Catalog, if you don't use schema, the data just looks like byte messages inside Databricks and Snowflake, so you really don't end up with usable data in that case. Because when you're writing in byte data, you're typically going to then consume the data in another streaming application, which then knows what object to deserialize it in. But when you're going to use Snowflake Open Catalog or Databricks Unity Catalog, you want to make sure that you use a schema, because it actually will then create the data in the columnar format, or in the columns readable in tables out of Snowflake. So you can do your SQL queries, run your Python on the fields automatically. So yeah, you definitely want to be using schema, I think, when you're using the catalogs as well, because then the schema will be registered with the catalog, and the data is queryable very easily by those fields. I think that's all we have for today. Thanks everybody. Oh, Matteo, go for it.
Yeah, I wanted to do sorry, one follow up on the second questions about the cost latency. And so I think what InterCentral can turn on and off to improve latency. And one thing that I want to add is that we are also working on a lower latency version of Ursa that is going to get out soon enough. But essentially, we're going to bring all these advantages that we described, the lake house and the leaderless and all these kind of improvements we did in the Ursa engine to lower latency kind of workloads that would be as low as a classic Pulsar and engine. So there's stay tuned there. We have some announcement down the road on this front.
All right, sounds good. Something exciting for me to work on too, and
yes,
make demos for. Thanks everybody for attending. Again, if you have any questions, I would encourage you to use this book a demo link, and someone will reach out to you, and we're more than happy to help you get your BYOC set up, as well as show you how to run the benchmark test. And also our sales team with the book a demo link would be happy to discuss your specific use cases to make sure that you're using the right technology. So thanks everybody again for attending. Thank you, Matteo and Pengwei. And hope everybody has a great rest of their day. Thank you.
Thank you. Bye.
Bye.